Hi there, my name is Christopher Worst and welcome to the second video for Homework 5, which is going over adiabatic flame temperature. This video is going over parts 2 and 3 because there's not a great starting point or stopping point between them and they kind of flow into each other. Part 2 asks us to start from the energy balance equation and derive the equation to be solved to determine the adiabatic flame temperature. And then part 3 asks us to derive the expressions to calculate the ideal gas enthalpy for each species as a function of temperature, showing the ChemCat expression for Cp, which is the heat capacity, and then integrating this from the standard state temperature to the desired temperature T. We'll be using Wolfram Alpha as well, and then running our own function in Colaboratory, which I already have pulled up, and using that. So let's begin running out our equation. So, because this is an adiabatic flame temperature, the energy change of the energy loss is equal to 0. So the internal energy and enthalpy is equal to 0. Or the change in U, or the change in energy, is equal to the enthalpy at state 1 minus the enthalpy at state 2. Of course, this is 0. So the enthalpy at both states are equal, as shown here. So, with that being said, this equation can be written as the change in H, or change in enthalpy. Now the change in enthalpy has its own equation, is equal to the change in enthalpy divided by the change in time at a constant pressure, so that's the rate of change of enthalpy over time at a constant pressure, multiplied by the change in temperature. Now this function, this change in enthalpy over time at a constant pressure, is commonly referred to as Cp, or the heat capacity at a constant pressure. So this can be written as the change in enthalpy is equal to the heat capacity multiplied by the change in temperature. Now over small changes in temperature, you can simply have delta H, the change in enthalpy, be equal to the heat capacity multiplied by the change in temperature, and I will make this less crooked. That's better. So we have that, but that's only over small changes. So let me move over here to do large changes. For large changes, you need to take the integral. So the integral of H of, not T, and of H is equal to the integral of the heat capacity with respect to temperature. So this means that H2 with starting at heat or enthalpy at state 1 and going to enthalpy at state 2. That means that enthalpy at state 2 minus enthalpy of state 1 is equal to the integral from temperature 1 to temperature 2 of the heat capacity multiplied by the change or heat capacity dt. That means that the enthalpy of state 2 is equal to the integral of the heat capacity from temperature 1 to temperature 2 plus the initial enthalpy of whatever the compound is that we were using. So if we take the integral here of Cp with respect to T, we can find the second enthalpy, assuming we know the first enthalpy of number 1. Now, we're going to be using our computer because there are multiple equations and websites, especially Wolfram Alpha, that we can use to make this integral much, much easier. So let's start with that. So part 3 is asking us to use ChemCAD to find CP, which is actually equation 107 on your screen here. So the heat capacity is equal to A, B, C, D, and E are all constants or coefficients that are specific to the different compounds that are used. So the heat capacity is equal to A plus B multiplied by the coefficient of C divided by temperature divided by the hyperbolic sine of C divided by temperature, and that quotient is squared, plus D multiplied by, again, the quotient of E over T over temperature, again, divided by the hyperbolic cosine of E divided by T, and that quotient here is squared. So A, if you use an integral for a constant, is of course just going to be AT, but these two, the C, specifically the hyperbolic sine and the hyperbolic cosine, are a little bit more difficult. So we're going to be using Wolfram Alpha instead of doing it by hand. So we don't necessarily need to put B in, although I will anyways. B multiplied by C divided by temperature divided by hyperbolic sine of C divided by temperature, that is squared. We're using comma T to input that T is our integral coefficient or integral variable. I want to make sure I've got that right. B times C divided by T. Yes, okay. I hit enter, that should work. Yes. Now cotangent, hyperbolic cotangent works like cotangent, excuse me, is just 1 over the tangent. So we'll be using the 1 over the tangent in our code instead. And then I will also integrate the D. So D multiplied by E divided by T divided by the hyperbolic cosine of, again, E divided by T. This is squared. We're using T as our variable. If we use that, E times negative D, hyperbolic tangent, E over T. Hey, we have our two, not consonants, but we have our two integrals. So now we can code that into Collaboratory. So now we're going to take this specifically and just swipe over to Collaboratory to program out two functions to find the integral of the heat capacity as well as the enthalpy at a certain temperature. So to do that, I'm going to first open up something. Open. I want this homework because I'm going to swipe something from it. I'm going to swipe its first line, this line here. Just going to copy and paste this. Cancel out, paste. Now what this is doing is taking this GitHub link depth. There. Don't need this anymore. Anyways, we're cloning this link into our code or into our thing. So now we have our CHE tools. So now we can look at whatever we want, whatever properties we want. So now we need to import a few things. So first of all, we're going to import sys. We're going to use sys.paths.insert one, and we want a string, and I think this is not paths, but path. We want to insert a string, content, CHE tools. Import sys is we're importing our system in order to, it's a module to manipulate where we put things in our, not code, but in our files so that we can more easily access this content specifically. We also want to import numpy as np, again, numerical Python, the usual. We're going to be using it. Specifically, we're going to be using arrays. We also want to import scientific Python, specifically optimize, because we want, or from, we want root. Import root. No. We want root for later so we can actually take our equations and find, specifically our matrices, and find the temperature at the very, very end. We also want to import tools.che as che. If I hit Shift Enter, that should work. Good. I don't know why this is giving me a yellow. Should be fine. Either way, we are now going to create a variable that is specifically meant to house the properties of our different compounds. So remember from part 1, we had methane, ethane, propane. In a combustion reaction, we also have oxygen, carbon dioxide, water, and nitrogen, which is carried through. That should be it. Yes, okay. So we want actually now che.props, or we're using our che tools now to get the properties. And from it, we want to make an array. So because this array will now be used throughout the code to get the heat capacity and get the enthalpy of everything in this array. So we're starting off with methane, moving on to ethane, then propane. Going to use oxygen, which needs to be a string. I like to hit enter because I need to move it down so it doesn't run out of room. Nitrogen. We want carbon dioxide, which is one word. And we also want water. Now, propane specifically needs to be N-propane because there are multiple types. There are multiple types of propane. So with this, we now can pull in our properties. And this order is important because it will put the array in order of methane first, then ethane second, then propane, oxygen, etc., for manipulation later. So with that, we can shift enter. Carbon, forgot to capitalize it. There we go, much better. So now we're going to create a function in order to, as you can see in the equation, in order to get the enthalpy of some temperature T, we need to integrate our heat capacity. So I'm going to just call our function integrate CP, and then we're just simply going to return. It's not a complicated one, but we're going to return our integral. So now we're going to be using our props, or properties, because there is specifically, and I'm just going to call it ethane. We'll look at ethane. Don't need this. I'm just showing this. If we look down, we have melting point, we have heat of formation, which we'll be using later. We also have, if we look at this, look down, solid density. Here we go, ideal gas heat capacity, which is going to be referred to as P.Cp, heat capacity, Ig, ideal gas. That's looking for joules per K mole per K. Now, if you look later, we're going to be using kilojoules instead, so we're going to divide our total thing by 1,000, but that's not important right now. But you see that there are these coefficients here, A, B, C, D, E, F, and G. You notice that these are what we need for our integral. So we have P dot Cp Ig, again, heat capacity, A. We want A. This is multiplied by T. Plus, now we're going to be taking P dot, again, now we want B multiplied by, we want C divided by, this is the hyperbolic tangent, numpy dot tan H. Good, that shows up. And now we want, again, the properties, we want the heat capacity of, we want C again, and this will be divided by temperature. And then we want to subtract, because if you look at this, this is negative, E multiplied by D, so we'll just do D. P dot, the heat capacity of an ideal gas, we're using the D coefficient, multiplied by the E coefficient. And then this is going to be, again, multiplied by hyperbolic tangent, which is a numpy, so NP dot hyperbolic tangent of the heat capacity E divided by temperature. So that should be good. We have now our, and I can get rid of this, we now have our integral function created and returned out, so it'll give actual values. Now, we want to define another function, call it h of t. This is just looking for the enthalpy. And we want it to return, and if we look here, we want the integral from t at temperature 2 minus the integral at temperature 1 plus the enthalpy or heat of formation at state 1. So this is going to be P dot heat of formation of an ideal gas plus, we want now integrate Cp at temperature T. We want to minus our initial temperature, which if I look in the homework, shows 298.15. 298.15. Now if I hit Shift Enter, it runs. It doesn't give any values, but if I give, say, 300, a short increase, it gives an array. Look, this array here shows that the enthalpy at 300 degrees is negative 8,796 for methane, etc., etc. Now, I did mention before that we had to divide this by 1,000 because of units and making sure that they all match up. So now if we use this, these increase by quite a bit. It's now about 7,000, 8,000, or sorry, 70,000, 80,000. These are joules instead of kilojoules. So we now have that, and from there we can get on to part 4, which a little bit of a key thing is simply just finishing up our code, coding our model, and then solving for the temperature to finish up. So, thank you very much for watching, and I hope you have a wonderful day.